My name's Andrew. I'm one of the co-founders of CircuitHub, and I'll be joined shortly by my colleague, Ollie Charles, who's one of our software engineers. We're going to talk about manufacturing circuit boards with robots and Haskell. So I'm just going to start by giving you a quick bit of background on CircuitHub to set a little bit of context. Then Ollie's going to jump up here and show you how we do some cool stuff with robots using Haskell. So I think you can probably consider this, it's not a deeply technical talk, it's more of an experience report of how we use Haskell in a real-world production environment and actually generate business value doing that. So our mission at CircuitHub is to make it really easy for electronics engineers to get circuit boards manufactured. So circuit boards go into all sorts of different types of products. The types of things that you're probably typically familiar with will be computers, cell phones, TVs, sort of mass market consumer electronics. That's not something we really get involved with. It's much more about the niche applications. So there are hundreds of thousands of different technologies that all require circuit boards and probably some sort of software in them. So a few examples here: underwater drones, Mars rovers, particle accelerators, 3D printers, and self-driving cars. That's really more the end of the spectrum that we get involved in. Now, we produced a little example here for the conference. So this is a design for a circuit board, obviously in the shape of the Haskell logo. So we designed this ourselves, and then we ran it through our own manufacturing platform, and we made about 30 of these. We've been giving them out on the stand today, so some of you may already have these available. But I think we've got a few more left, and they don't do anything particularly useful. But if you click this button here, they sort of light up in quite a pretty way. So if you want one of those, come and speak to us afterwards. We've got a few left on the stand. So if you're an electronics engineer, you design circuit boards using what's called an EDA tool. So this is an electronics design automation tool. And this allows you to input all of the design intent for your circuit board. So that's going to include the logical representation in terms of the schematic, the physical representation in terms of the geometry, and typically the bill of materials, which are the different part types that you're actually going to use on your circuit board. So you can capture all of that information using this desktop tool. You then save that out into typically a couple of files. So that's going to be a schematic and a circuit board. You can then upload those files onto CircuitHub.com. And we use Haskell to parse those files and normalize them into a database. So this data is supplied in a very messy format, and Haskell allows us to clean that up into a consistent format. We then pass that over to another service written in Haskell, which is our pricing engine or our quoting engine, and it takes that normalized data, which includes all of the significant features about the circuit board, so the geometric information, logical information, the bill of materials. We crunch all of that data, and we use it to generate a price. So we ask the electronics engineer two questions: how many units do you want, and how quickly do you want them? From that, we get pricing information. Then you can click an order button. And that's really where it gets interesting, because we then have a factory on the back end where we're able to automate that manufacturing process. And this, of course, is also driven purely by Haskell. So Haskell, really does power all of our front-end user-facing applications. We have a pretty extensive set of internal applications that are used by our production engineers on the shop floor. And we also do some pretty cool things with robots. So I think, unfortunately, the secret's out for some very familiar faces in this room. So I think a few of you have perhaps seen this already. But Ollie's going to jump up and give you a little bit more detail on how we use Haskell to control robots.
Cool. Cheers, Andy, and hi, everyone. Hopefully a bunch of you have had a chance to see this already, but maybe for those of you who haven't seen it or people who are viewing from home, this is what we've had set up during the last couple of days. So up in the top right here, we've got a live view into our actual production factory. And we've got a little robot here. And down in the bottom, I've got a little GHCI REPL that allows me to interact with this robot. So I can send commands to it. So here I've got a little command. I'm just going to say pick up panel 5. And you can see then that gets sent live over to the robot, and it then begins picking up this panel. So that's not a very interesting command. I mean, it's quite useful, obviously. But this REPL and this system that we're working with is actually a little bit more intelligent than this. So it says, what should I do next? And I'm just going to ask it to do exactly the same thing. And you can see here, the robot decides that it doesn't actually need to do anything, because I asked it to pick up panel number 5, and it still happens to be holding panel number 5. So there's a little bit of memory happening behind the scenes here. But this next command is a lot more interesting. Now I know that I'm holding panel number 5, but I want to move panel number 1 to slot number 5. So this is actually a little bit more interesting. I can't simply just pick up panel 1 and move it to slot number 5, because that would require I use the robot, and the robot is already holding a panel. So here we can see that there's what's called a planning engine has figured out that the first thing I need to do is load one of the slots. So these are called bay slots where we can put circuit boards. I'm going to load slot number 10 with the circuit board that I'm currently holding. Then I'm going to move over to slot number 1, pick up a circuit board from there, and then finally I'm going to move over to slot number 5 and put the circuit board there, because that's finally what the user actually intended. So this is not exactly what we use in the factory, of course. We don't just have GHCI terminals lying around. We've polished this up into some actual applications that live on part of an internal website. But it's still using a lot of the same actual production code that we use, and certainly that planning engine is something that we use in the factory. So you can see there it's now picked up the circuit board that we're interested in, and it will then finally move that over to slot number 5. So I just wanted to kind of peek behind the curtain and show you what's actually happening when I run this interesting command here. So execute, move panel 1 to slot number 5, in that state where we're already holding a panel. And generally, there are 3 steps that have to go into solving this problem. First of all, we build an internal model. So I need to understand where panels currently are in order to come up with a solution. I also need to know how I can change the state of the world. So I need to know that I can pick up panels, and I need to know that the robot is capable of putting panels back in the work cell and into the slots. Next, once I've got this internal model, I feed that into some kind of planning system and come up with a plan. How am I going to move panel number 1 to slot 5 based on what I know? And then finally, I'm going to execute that plan, which means sending those commands over from our GHCI REPL to the actual robot to affect the real world. So I don't have time to go into the details of all of those steps, but I just wanted to hone in on this step number 2, which is coming up with a plan, because that's where I think the really interesting work happens. So to come up with a plan is to solve what is called a planning problem. These are general classes of problems that are well studied, and they're applicable in all sorts of different domains. Essentially, a planning problem is where I have some known deterministic system, so I can model the states that the system can be in at any point in time, and I know how to transition between those states. In this case, we're going to solve the planning problem by translating it into a graph search problem. So that's an even richer domain where we happen to know how to solve graph search problems. There's a lot of algorithms we can take there. And in this case, every node in our graph is going to be a distinct state that the factory could be in at any point in time. So in the example here, the factory is really just a collection of circuit boards and places you can put them. In CircuitHub internally, the factory is a lot more complicated than that. So we model the various machines we have, the state of the circuit boards as they go through production. And the edges in this graph correspond, again, to those transitions between the states. So I could pick a single circuit board up, or I can apply solder paste to a circuit board. Those correspond to atomic independent state transitions. So the edges between those move us between these atomic actions, and planning problems are now graph search problems. So I know when I built the model, the initial state of the world, and I'm interested in finding a minimal path that will take me from that initial state or that initial node to some other node in the graph that satisfies what's called the goal criteria. So I want to be somewhere in the future. The interesting thing is these are generally really, really big graphs, almost incomprehensibly big. You only need a couple of little bits of state to interact, and you start producing hundreds of possible states. And really, in the case of CircuitHub, we're talking about billions of possible states that we could be in at any point in time. So simply using a naive algorithm like a breadth-first search or a depth-first search isn't actually a tractable solution at all in any meaningful time frame. So we need to be a little bit more intelligent. So we did a little bit of research and worked out what is an appropriate way to search one of these graphs, and we came across a general purpose solver for planning problems, which is called fast downward. So I said here it's used for state-of-the-art research in planning problems, and so the planning problem domain has been under research for about 20 years, and it's still definitely not solved. But the nice thing is, because we're using this general-purpose planner where new research is happening, as new solutions are discovered, we get to benefit almost for free at CircuitHub, which is quite nice. It's distributed as a C++ executable, which is not great for us, but it does have a well-documented input and output format, which means it's very appropriate to target with a domain-specific language. So we built a little Haskell domain-specific language to interface with this executable using some very idiomatic Haskell concepts. Unfortunately, I can't really show you any code because we're a bit limited on time, but it's essentially like the STM library for software transactional memory. So STM has transactions that can read and write to variables. In this library, we have actions or effects that can read and write to the state. So once you have this little API, we can then use some very familiar Haskell concepts such as functor, applicative, monad, and monad plus to begin to model those state transitions. And the idea is I want to build a system that knows about all the independent actions that could happen at any point in time. And then I simply ask the planner, which of these should I do? So if you're more interested in this, it's freely available open source software on Hackage, so you can just grab that and try that out in your own problem domains. I've got a blog post from last year that explains solving a small kind of prototypical problem using fast downward. And I also gave a little talk at MuniHack earlier this year that it talks about planning problems and shows how to use this fast downward API. So let's just finally wrap that up and see what these 3 steps look like for moving panel 1 from into slot number 5. So we first build an internal model. The internal model of this factory is really quite simple. We just need to know where are all of the panels. So I know panel 1 was in slot 1. I know panel 2 is currently in slot 6. I know panel 5 is currently in the robot, and so on. And I also have to work out all those actions that I can apply. So that's essentially just enumerating a set of known actions. I then feed this into the planner to come up with a plan, and in this case, the planner tells me, okay, I'm going to load slot number 7, then I'm going to pick up the panel that's currently in slot number 1, and then I'm going to load slot number 5. And then I need to execute that plan. So the planner gave me a very high-level description of these independent actions, but the robot doesn't understand what those mean. So there's essentially a compilation step where we move from this high-level description of picking up the panel in slot number 3. We compile that down to what is essentially a function call on the robot. So the robot has a Python-like scripting language, but it has no database access or knowledge of the physical dimensions of what it's actually picking up. So we just give it a bit more information here, which is I want you to pick up the panel in slot number 3, and here's the midpoint of that panel, so that's where you should actually grab it from. So we have essentially a combination of some hard-coded coordinates, but we can kind of augment that with some extra information from our own internal database. So that's the idea behind the planning problem that we've been demonstrating just in the booth. We actually use this in a much larger context in CircuitHub. So all of the machines in the factory have Haskell APIs, and we can integrate all of these into a planner, which allows us to do planning over multiple machines. So I could ask a circuit board to be moved from the current location and placed into a machine. And if there's already a circuit board in there, that can automatically be removed. And the good news is, we are hiring, which to me is fantastic. It's going to be fun. If you're interested in any of these problems, definitely give us a shout. I think we're going to be around for the rest of the day. And we do plenty of other cool stuff as well, so feel free to grab me. Thank you.
Okay, we've got a couple of minutes if anyone's got any burning questions. Okay, you're all free. All right, we'll grab a refreshment. We'll see you for the keynote.
We have beer tickets.